All right, welcome everybody. So in case you haven't found out yet, this week we have our first exam, and our first exam is going to be this Wednesday evening, and it's going to be over proctored over HonorLock. So I think most of you guys have probably had experience with that at this point. So hopefully you know the situation on how that works. What we're going to be doing today is I'm going to be going over this old exam, so from spring of 2018, and this was also written by Dr. Huang, so it should be relatively similar to the type of exam that she writes. And yeah, we're just going to go over the questions from this today. I'm going to work them out, give you full solutions, and then whatever questions we can't finish today, I'm going to record a second part to this video tomorrow where I finish going over this exam. And if I'm not mistaken, I think Dr. Huang is, if not, she hasn't already, she's making a video where she goes over a different exam. I think it's from 2017 or something like that. You could also check that out on the Canvas page. All right, and where can we find the link to this test? It should be under exam information on the Canvas page. So you can follow along on there if you'd like. All right, let's go ahead and get started. There's not really a lot of room to work in here. So I'm gonna have the problem like maybe right here. And then I'm going to do my work like right here. Yeah, let me get rid of that. There we go. I had to minimize the participants list so people here could see that. So if you raise your hand, I'm not going to be able to see it. All right, anyways, let's go ahead and get started here. So given a point A, which is -2, 3, and -4, which of the following is /R correct? So we have three options here, and then they have the different combinations of options right here. Okay, so let's take a look. So we have our point A, -2, 3, -4. Okay. So then let's see what we got here. The first statement says the distance from A to the x-axis is going to be 5. All right, well, let's see. So the x-axis, that has the equation y = z = 0. And technically, these are a really stupid form of symmetric equations. It's kind of funny looking. But yeah, so this is just saying that we can have whatever x value we want for our point, but we can't have y or z be anything other than 0. So if we want to find the distance to this, we don't really care what x is. X can be anything we want, but we will do 3 - 0 squared. So we have 3 there. And then -4 - 0 squared. So we can get the distance to the x-axis here. All right, well, let's see here. So this is the square root of 3 squared plus 4 squared, which is √25, which is 5. So it says the distance to this is 5, and that is absolutely true. So we know that only these answers could be correct because we know P is true. And don't forget to do things like that. Since a lot of this exam will be multiple choice, don't forget to use just basic logic to help narrow down your answers in case you do run out of time. All right, let's check out Q here. That's statement Q. The distance from A to the XY plane is 4. All right, guys, so what is the equation for the XY plane? It's a very simple equation. Z = 0 is correct. Okay, and this is the only requirement for this plane. X and Y can be any value we like. We just need Z to be 0. So if we look at the square root of -4 - 0 squared, this is going to be the square root of 16, which is 4. So that's going to be our distance for this right here. All right, so we know this is true. And actually, we don't even technically need to look at R because there's only one answer that satisfies this. It's going to be P and Q only. Why don't we go ahead and just see why R is false, though, in case we didn't have that luxury on the real exam here. So this is saying the distance from A to the plane x = 1 is 1. All right, so kind of like how this was Z = 0, and that was the only requirement. The only requirement for this one is x = 1. So for R, we want to find the distance to x = 1. So we do the square root of -2 - 1 squared, which is the square root of 9, which is 3. But unfortunately, 3 is not equal to 1. So this statement's going to be false right here. All right, so there we go. So we got this one all correct here. And don't forget to use basic exam logic as well. That'll certainly help you out. All right, let's move this up a little bit. All right, our next question here. So the lines 1 plus 3t, -1 and 4 minus 3t, and 1 plus t, 1 minus t, and 2 intersect at this point. What is the angle between the two lines? Well, all we need to know to get the angle between two lines is what their direction vector is. And then once we know what their direction vectors are, and then once we know what their direction vectors are, how can we figure out the angle between them? Anybody know? Yeah, we're going to use the dot product. That's right. So let's figure out the direction vectors for this line. So let's call this line 1. And we can call this line 2 right here. All right. So let's see here. I'm going to call V1 the direction vector for line 1. So can anyone tell me what the direction vector for line 1 is going to be? 3, 0, -3. That sounds pretty good to me. And how did we get that? We just read off the coefficients of t. And if there isn't any t, then this is not going to be changing at all. So we're not going to be changing in the y direction. So we have 0 right here. All right, there's V1. And V2 we can get in the same manner. We read this off and we have 1, -1, and 0. Like that. All right, and then all we need to do here is do the dot product between these two. And remember that that's going to be the magnitude of V1 times the magnitude of V2 times cosine of the angle between them. So if we do the dot product and then we divide by these magnitudes, then we'll get closer to having the angle between in there. All right, so let's see here. V1 dot V2, what's that going to be? Well, we have 3 times 1 is 3, 0 times -1 is 0, and then this times 0 is 0. All right, so it looks like we just get 3 for the dot product. The magnitude of this will be the square root of 9 plus 9. I'm squaring both of these. So it's going to be the square root of 18. And then finally, the magnitude of this, if I square both of these, I'm going to get 1 for each of them. And if I add them together, I'm going to get 2. All right, so it looks like cosine of theta is equal to 3 over these square roots right here. Well, root 18 times root 2 is root 36. And conveniently, that is a nice number. That's going to be 6, meaning that this will end up being 1/2 right here. All right, so then let's see here. Remember, cosine of theta is our 1/2, right? So what is the angle that matches, that makes cosine be 1/2? Pi over 3 is correct. All right, and there we go. So there's pi over 3, and that is one of our possibilities here. It's always encouraging when your answer shows up on the list right here. All right.
Dr. Manley, I have a quick question.
Yeah, what's up?
I tried to simplify root 18 to 3 times root 3. Was that totally wrong, or?
It'd be 3 times root 2 because let's see, root 18 is 9 times 2, and then you can move the 9 out there. So it'd be 3 root 2.
Okay.
And then those we combine together.
Thank you.
One thing I want to point out here is that it says they intersect at the point 3, -1, 2. That was irrelevant to this problem. We did not need to use that information whatsoever in order to get this answer right here. All we needed to know was their direction vectors. Meaning if you kind of slid one line, like let's say originally they were doing this, right? Let's say we kind of slid this line down this way and they intersected at a different point. The angle between them doesn't change at all right there. So the specific point where they intersect is actually irrelevant to this question.
Dr. Manley?
Yeah, what's up?
So in that intersection, there are 2 different angles, and sometimes it'll ask for like the angle between 0 and pi over 2. How do we like know which angle is which?
There are 2 different angles. Are you talking about like theta could be like negative pi over 3 or something?
I mean, like in that intersection that you drew, you have an acute angle and an obtuse angle.
Oh, I see what you're saying. So how do we know whether we want this one or this one? They want the acute one. That's
Okay,
that's
thank
how it's
you.
going to be. All right. Let's go on to the next one here. So the next one is going to help us review something called vector projection. All right, let's see here. I'm starting to run out of room on this page. Let me get a new page here. All right, so I'm going to write up here now. Oh, actually, no, I don't want to do that. Where's the end of this paper? I can't even see it on here. All right, there we go. I'm going to write up here. All right, in the following picture, u, the vector u, is 2, 4, and 5. And the vector v is 1, 1, and 0. So we want to find the vector w based on this picture right here. All right, and let's take a look at this. So we have this u, right? And then we have this v down here. And it seems like w is going to be perpendicular to v right here. So remember back from one of the earlier lessons that we could always break up a vector into two different components relative to another vector. We could always write u as u parallel plus u perpendicular, where parallel and perpendicular are referring to how it is relative to v right here. So we could have one piece that's going to be parallel to v, and then one piece is going to be perpendicular. So the shadow of this, the projection down to here, is going to be this vector, and this is going to be u parallel. And our w here will end up being u perpendicular. So what we could do to get u perpendicular, or w, is we could find out what u parallel is, and then we could just subtract it from u right here, and that will give us a remaining piece. So what we're going to do is we're going to do u minus u parallel, and that's going to give us w. Now, u parallel has another name. Does anyone know what the other name for u parallel is? How do we get a vector that's based on u that's parallel to another vector right here? It's the projection. That's right, very good. So another name for this u parallel is the projection of u onto v. This is a v right here. Let me rewrite this. U minus the projection onto v from u. Okay, so we already know what u is. That was a given piece of information here. But this vector projection here is something that we know how to figure out. So we can just figure what that is, and then do some subtraction. So the formula for this is going to be v dot u divided by the magnitude of v squared. And remember, this is all a fancy scalar, and it's going to be in the direction of v right here. All right, well, let's see what's going on here. So let's do u dot v first. So that's going to be 2 times 1 is 2. And then 4 times 1 is 4. And then 5 times 0 is, well, 0. Okay, so that's our u dot v. Now the magnitude of v, let's see. So we have 1 squared plus 1 squared is 2, but then that's all under square root. So the magnitude of v is root 2. But then remember, we're squaring this right here. So we're going to get 2. And then finally, our v, this is just our originally what v is, we have 1, 1, 0 right there. All right, well, let's do some arithmetic here. 2 plus 4 is 6. That I divide by 2, and I get 3. 1, 1, 0. And so that means that our vector projection is 3, 3, 0, like this. All right, now remember, our original objective wasn't to get the vector projection, it was to get the thing that's parallel to this right here. So how do we get that? Or sorry, perpendicular. We're trying to get w here. So how do we get that? We just do u minus the thing we just got. So we have 2, 4, and 5 minus 3, 3, 0. All right, 2 minus 3 is -1. 4 minus 3 is 1. 5 minus 0 is 5. So that means that this vector right here is going to be negative 1, 1, 5 right here. So that looks like that's going to be answer E for this one right here. Is there really a point in square to the magnitude if it's squared? Yeah, so what you could do if you don't want to bother with squaring this is you could just square each of the components and then add them together. Or equivalently, you dot the vector with itself. Yeah, you could just do that instead of taking a square root and then just immediately undoing it if you want. All right, so there we go. So that was a really good practice with the vector projection here and decomposing vectors into their parallel and perpendicular components. All right, let's see here. So let's go on to our next set of questions here. All right. So the vector AB2 is perpendicular to the plane z equals 2x minus 3y plus 1. What is the value of A? And they have the dreaded insufficient information to determine this answer. Now, in terms of exams, like most of the time that's not correct, but sometimes it is. Sometimes they really don't give you enough information to solve the problem. So you can't entirely rule this one out. Let's see if this is one of those problems. All right, so we're saying that this vector, which I'm just going to call V, V is A, B, and then we have 2 here, and it's perpendicular to this plane. Now, what I'm going to do is I'm going to move everything to one side. So I have negative 2x plus 3y plus z is 1. Well, you could have it equals 1, or you could have minus 1 equals 0. It's actually not going to matter for this one right here. All right, so why did I do this? Why did I put everything on one side right here? Well, this lets me read off the normal vector right here. So the normal vector for this plane is negative 2, 3, and 1. Okay, well, that means, remember, if this is the plane right here, let me draw this. This is our plane, this is our normal vector, right? And normal is just another name for perpendicular. That's what it is. So if we have a vector that's perpendicular to our plane, that means it needs to be parallel to our normal vector. It could just be a different length, but it's going to point in the same direction. So that means if we have a z component of 1 here and a z component of 2 here, and we need these to match up with one another or be parallel, then what does that say about our A component right here? What does that mean it has to be? That's right. So since this is 2 times that, and this needs to be parallel to this since they're in the same direction, that means we're also going to multiply this by 2. So A ends up being negative 4 right here. All right, good. So that's going to be our answer for this one. It's going to be negative 4. So we did have sufficient information for this. And once again, we have some irrelevant information. It didn't matter in any way what that B is. I mean, we could easily figure that out too. It's going to be, let's see, it's going to be 6 here, 2 times 3. All righty. I think I saw a question in the chat right here that I wanted to answer. What if we decided to move everything to the other side? So let's say I subtracted z here, and then I had the normal vector 2, negative 3, negative 1. Could I still have done the problem that way? And the answer is yes. It's just that your multiplying factor right here would have been negative 2 instead. But you still could have solved it in pretty much the same way. How do we know if a problem is referring to the normal vector as the direction of the plane or as perpendicular to it? The normal vector is always perpendicular to the plane. The normal, whenever you have a plane that looks like this, the normal vector is always pointing out of it. So if you ever have something that says in the plane, it's not talking about the normal vector. So just want to be clear about that. Normal vector is always perpendicular to the plane. It's kind of confusing because with lines, we identify lines by having something parallel to them, but with planes, it's the exact opposite. We have something that's perpendicular to it. All right, let's move on to the next problem here. Let's see. Given 3 points, and they're right here, find the area of the triangle PQR. Okay, so we learned about one area formula before. It's that if we have vectors A and B, and we know this is AB sine theta, right? Then this is the area of the parallelogram made by A and B. So maybe if A looks like this and B looks like this, then the area of the parallelogram made by them is going to be the magnitude of the cross product right here. All right, now if we want to get the triangle made by these, we want to get that area, all we need to do is just cut this in half. So what we're doing is we're going to make two vectors, A and B. We're going to take the cross product of them, see how big it is, and then we're just going to divide by 2. That's going to give us the area of our triangle. So if they ever ask for a triangle's area, you do the cross product divide by 2. If they ever want a parallelogram, you just do the whole thing. All right, well, first we need to make our vectors A and B here. Then they give us 3 points, which is enough to make our, it's enough to make our 2 vectors here. So let's do maybe PQ. What's that one going to be? All right, so I have 5 minus 4 is 1. 5 minus 3 is 2. And 6 minus 5 is 1. All right, and then PR, what's that going to be? Well, we have 6 minus 4 is 2. 7 minus 3 is 4. And then we have 8 minus 5 is 3. These vectors are almost parallel, but this 3 kind of makes it a little bit different. All right, and then we just need to find the cross product of these 2, find the magnitude of that, and then just divide by 2. All right, I'm running out of room here. Can't write too far to the other side. All righty. So let's see, the cross product of these 2, I, J, K, like that. We have 1, 2, and 1, 2, 4, and 3. All right, let's do some cross product here. Let's see. For the I block, that's going to be these 4. We have 2 times 3 minus 1 times 4 will be 2. For J, we have 1 times 3 minus 1 times 2 is 1. But then remember, J gives us a negative. And then finally, for the K block right here, we have 1 times 4 minus 2 times 2. That's going to be 0. All right. Yeah, the negative actually doesn't matter. Oh yeah, the order for this doesn't matter. And actually, if you did forget the J negative for this one, that actually doesn't matter either, because we're just finding the magnitude of this vector. So this is the one time where you can get away with not doing that. Anyways, this is our cross product, and the magnitude of this, so the magnitude of PQ cross PR is equal to the square root of 4 plus 1. So it's the square root of 5. And then remember, we wanted this divided by 2. So the area of our triangle is going to be root 5, but then we divide that by 2. So that's going to be our answer for this guy right here. How do I know magnitude is going to be the absolute versus absolute value? If you want the area of something, it's definitely going to be positive here. So even if we did this the other way and got a, yeah, if you ever want area, it's just going to end up being positive here. All right, so let's move on to number 6 here. Let's see, number 6. All right, this one we need to think about a little bit. So, oh yeah, sorry, the magnitude of a vector will always be positive here. Yeah, so if you ever see absolute value signs around a vector, that's definitely referring to its magnitude. I don't know what I was thinking there. All right, so which of the following equations describe the line passing through the points 2, 0, 1 and 3, 3, 3? Okay, well, let's check this out. Oh, it's covered up. Oops. All right, let me move this up. There we go. Sorry about that. Okay. All right, so let's take a look at these lines. First of all, let's make sure that these lines are actually going through one of these 2 points here, because if they aren't, we can immediately eliminate that as, well, I guess we can't entirely eliminate it as an option, but we could at least be suspicious of it. So 2, 0, 1, I think this line goes through the point 2, 0, 1 for sure. And then so does this one, because we have -2, -0, and -1. And then this one is going to go through the point 3, 3, 3 right here. So we can't eliminate them based on that reason right here. Okay, now if they go through these 2 points right here, we know 2 points, so we should be able to find a direction vector for this line. So our direction vector, let's see, we could just do 3, 3, 3 minus 201. So it's going to be 1, 3 minus 0 is 3, 3 minus 1 is 2. All right, so this is going to be our direction vector for our line. And whatever direction vector they use in these equations needs to be parallel, or at least anti-parallel to this right here. Okay, so let's take a look. So the way we read off what the direction vector is going to be from our symmetric equations is we look at the denominator, so long as these coefficients are 1. So here, this line is going to have a direction vector. So I'm going to call this V1 for the direction vector of L1. This is going to be -1, -3, -2. Okay, and then this is parallel to V. It's actually just going the other way, but it's still going to hit all of the same points. So it turns out L1, yes, those will be symmetric equations for our line. Those are totally fine right here. All right. So next, what do we have here? We have 3, 3, 3 for our direction vector for 2. Okay, and I see where they get that from. They get it from this point, but the things down here aren't supposed to represent a point. They're supposed to represent the slope of our line. Oh, can we just plug and chug? Let's see here. So if you plugged in, yes, so let's see here. Could you do that? Oh yeah, I guess you could do that. That is a lot simpler than what I'm doing, isn't it? Yeah, you as long as these are the equations of the lines of actual lines, like they follow the symmetric line format. And if you plug in the other point, so like I plug 3, 3, 3 into this one and 2, 0, 1 into this one, that would be that would end up being okay. Wait, were you gonna say something?
No, I thought that it wouldn't work for line. It could work for.
Yeah, so if you plug in the opposite point to the one that's that they make the line based off of, then you could do that if you want to. But if you just plug in the same point, you're gonna get 0, 0, 0. Of course, you're gonna get that, but you don't know if it's still gonna go through this point though. So be careful with that. But yes, you can. All right, I'm just gonna keep doing this.
Professor, how did you find the normal vector?
I haven't found any normal vectors. I've only found direction vectors, and I found this direction vector by doing 3 minus 201.
Shouldn't all right, yeah. I thought that was an N. I'm sorry.
Oh no, it's okay. I just put a little thing on my V right there, yeah, like a little hook. Yeah. All right. Anyways, yeah, line 2 is not going to work because this is not parallel to that. And then V3 right here. Let's see. This is going to be 2, 6, and 4. And while it's not the same as this, or it's not even a negative, it is going to be parallel to this direction vector. So line 3 will work. So it looks like it's going to be line 1 and 3. And this goes to show you, this is just a gentle reminder that remember, there's a lot of different ways of expressing equations for the same line right here. Oh yeah, I see actually another way of doing this in the chat. What you could do is you could set all of these equal to t, find the parametric equations, and then see if you get the same parametric equations. That's another way of doing it as well. That's totally fine. So there's actually a lot of different ways of going off this problem. I just did the one where you can kind of read off the information from the symmetric equations without having to calculate. Well, I guess I calculate direction vectors, but it's mostly reading them off. All right, let's go to this next one here. If the curve C is parameterized by this vector value function, what is the rate of change of the arc length function when t is 1? All right. Well, remember, let's remember what the arc length function is. So we have that S of t is the integral from some number a out to t of the square root of x prime squared plus y prime squared plus z prime squared. And then I'm going to use du here since we already used a t. So this has to be a dummy variable because all these are going to be functions of u since we have t here. All right, now let's say I wanted to do the rate of change of this. Well, whenever we hear the words rate of change, that means derivative, right? So if I want to do s prime of t, okay, well, I'm doing the derivative of an integral, right? I think we know what happens with that. If we have the derivative of something being integrated, then you could almost imagine that these guys are canceling out, and we just end up with the function that's inside here. So we have the square root of x prime squared plus y prime squared plus z prime squared. And does anyone remember the physics name for this? What's the physics name for this quantity? Yeah, that's right. It's going to be speed. Okay, so effectively what this question is doing in disguise is they're just asking for the speed at t equals 1. So we don't need to do this integral at all. In fact, I think that integral really sucks. So it's good that we don't need to do that integral. They just wanted to know what the speed here is. All right, I am DST2. Nice one. All right, so let's take a look at this. So we have x prime. Remember, our functions here, the x is 1, the y is t squared, and the z is t cubed. So x prime is going to be 0 because it's a constant. Y prime is going to be 2t. And then z prime is going to be 3t squared. All right, so then that means that our speed is going to be the square root of, well, I guess 0 squared, so we don't need that. We have 2t squared, so that's 4t squared when we square the 2. And then we square 3t squared, so we have 9t to the 4th. And they didn't even really, wow, what am I trying to say here? Yeah, they're not even asking for this function. That's what I was going to say. They just want to know what it is in 1. So if we plug 1 in here, we have 4 plus 9, giving us the square root of 13 right here. So the square root of 13. I already know you would have tried to take the integral. Technically, you could take the integral, plug t into that, and then take the derivative of whatever you got. That is by far way longer than this, though. So yeah, it's definitely better to recognize this was the speed. All right, there we go. So we got square root of 13 for that one. So what did you have to know? You didn't have to know it. I just know that we've seen the name speed before, so I just wanted to remind you guys. Okay. Let's go to number 11. Let's see, how are we doing on time here? We're doing all right on time. Let's see, 2:28, good. All right, which of the following is an equation of the tangent line to the curve? R of t is all of that at t equals 0. Okay, well, let's see here. So in order to know what an equation for the tangent line to the
Dr. Manley,
curve,
we can't see the question.
oh, sorry.
It's all
It's
good.
kind of awkward having to like have it over here and then have this paper. Sorry about that. Wait, did I
We're
skip-
supposed to be on number 8.
Oh, I skipped a page. I was wondering why we were so far along in the test. There we go. Sorry about that. I printed off double-sided. Rip 8 through 10, really. Okay, let's take a look at this one. Consider the surface x squared minus y squared minus 4z squared is 0. Which of the following is /r correct? And there's another one of these things where you just have to check each statement. The traces in the plane parallel to the YZ plane are ellipses. Now, I want you to be really careful with this. I actually was going over this exam today to make sure I knew how to do it. And I was answering these questions by looking at this picture. But the thing is, this picture has to do with statement R, right? So we don't even know right now if this is the graph of our function. So don't use this for your information. Use only the equation up here. Don't get trapped into just using that nice picture. All right, let's go ahead and take a look at P. So P, the traces in the plane parallel to the YZ plane are ellipses. Okay, well, let's write down our equation. All righty. And then let's plug in, like, say, a constant value for the YZ plane. So something parallel to the YZ plane is going to have the equation x is some constant k. right here. All right, so let's go ahead and plug that in here. So we have k squared minus y squared minus 4z squared is 0. And if I add these guys over, y squared plus 4z squared ends up being k squared. And if we divide by k squared, we have y squared over k squared plus 4z squared over k squared. All right, and then what kind of shape is this going to be? This is going to be an ellipse. And of course, the size of this ellipse depends on what plane we look at, but it's going to be an ellipse no matter which value for k that we're going to pick right here. Okay, so we know that P is correct. That's going to be correct here. All right, let's check the next one. The vertical trace in the XZ plane. So notice it doesn't say parallel to the XZ plane. It says specifically in the XZ plane is two lines, X is 2Z and X is negative 2Z. Okay, so since they say in the XZ plane, that means we're going to use Y equals 0 specifically. So the XZ plane, or Y is 0. All right, let's put that in here. So we have X squared minus 4Z squared is 0. And then that gives us X squared is 4Z squared. And then when we take the square root, we have X is plus or minus 2Z. And that's exactly what they claimed we would get right here. All right, so we know that's going to be true as well. We're going to get these two lines that intersect like this. If this is X and this is Z right here. All right, and then finally, the graph of the surface is this. And effectively, it's just, this problem is asking you to identify what shape it is. So what type of shape is the graph describing right here? What's the name of this shape? Is this shape a cone? I'm not so sure about that. Yeah, this is the hyperboloid of two sheets. That's right. So notice it's almost a cone. If they both kind of reach out a little more, it'll be a cone, and they're a bit more straight. But yeah, this is a hyperboloid of two sheets. And remember, the hyperboloid of two sheets has two negatives for the squares, so it doesn't match this. But there's a 1 on the other side of the equation. There isn't a 0, there is a 1. So that means that this cannot be a hyperboloid of two sheets. This would need to be 1 instead. Then it would be that. What is it actually? What shape is this really going to be? Oh yeah, it looks like you guys have already been talking about it. Yeah, it's going to end up being a cone. And we can see that by adding the y squared and z squared parts to the other side. Remember, where we have 3 squares and then 2 of them add to be the other one, this is going to be a cone. So that's what this is going to look like rather than a hyperbola of two sheets. So this one's false. And we get
Dr. Mann,
yeah,
I have
what's
a
up?
question. Why did you plug in K for X, but then when you check the XZ plane, you plugged in 0 for Y?
That's because in this one, the first one, they said parallel to the YZ plane. So that could be any X value. But in this one, they specifically wanted in the XZ plane, which is specifically Y equals 0.
Yeah, that makes sense. Thank you.
All right, let's move on to the next one here. If we have this curve right here, then this curve must lie on the surface. Now, effectively, what we're going to do with this one is we're going to kind of take the spirit of what someone suggested for the other problem. We're just going to plug in this to each of these. So why don't we try A here? Let's try A, and we're going to plug in these parametric equations into here and see if it works. All right, so let's see here. For A, we have x squared plus z squared is 4y. Okay, so x squared is t to the 4th. Z squared is going to be 4t squared sine squared of t. And then the other side, 4y, is going to be 8t cosine of t. And unless there's some kind of bizarre trig identity that I'm unaware of, this is not correct. These two sides of this are not the same function. All right, so it's not going to work with A. I guess we'd normally move to B, but I'm just going to look at D since it's right below it. All right, so we have y squared plus z squared is 4x squared. Let's try that one. All right, so y squared is going to be 4t squared cosine squared. 4t squared sine squared for the z squared. And then we have 4 times t to the 4th here. Okay. Ooh, so this one's actually almost right. So with the sine squared and cosine squared, this side's going to simplify to be 4t squared right here. But then we have 4t to the 4th over here. So this is incorrect, but it's almost right. That means we should probably try to look for an equation that's similar to this. So let's see, let's look on our list here. All right, here's one that's pretty similar. We just have the same thing, only we don't square the x. So let's take a look at C. All right, y squared, we have y squared plus z squared again, so we already know that's going to be 4t squared. And then on the right side, we have 4 times x, which is t squared. All right, so there we go. We end up getting something that satisfies the equation here. Now, if you didn't want to just entirely guess and check, how could we have maybe simplified this and not wasted our time guessing on incorrect ones? Well, I see a sine and cosine pair here, right? And they have the same coefficient in the front. So that says to me, if I square those and add them together, that's going to do something nice. So since this was the y component and this is the z component, I could pretty much immediately narrow it down to one of these 3 options right here. And then I kind of just have to see which one matches the specifics of the problem. Kind of like how this one almost worked, but we just had our power too high. So then I just tried the one with the lower power right here. So that's a bit more of a rigorous approach. You just kind of recognize that there's a Pythagorean pair right there. Whenever you see a sine or cosine in something, try to see if you can get them to cancel out. All righty, that's good. Let's move on to number 10. All right, this paper is comfortably done. Oh, sorry. Here, I'll box that. I accidentally circled all of them. Yeah, that one's the correct one. All righty. Let's go to our last one here, or the last one on this page at least. Okay. So the path of a particle parameterized by time is this. Find the curvature of the particle's path at 1, 2, 1. Okay, so r of t is t squared 2t and t. All right, now let's see. So this is one of the ones where they give us a x, y, z point, but they don't give us a t point. So we need to figure out which t value is compatible with this right here. So which t value does this match up with? There's only one. Yeah, it says t equals 1. If you start here, you might be like, oh, well, it could be -1, but then -1 doesn't work with these guys. So it's going to end up being t equals 1. All right, now that we know that, now we just need to use the formula for kappa, or curvature, to get our answer here. Okay, so kappa of t is going to be r prime cross r double prime divided by r prime cubed. All right, this is usually the one I kind of default to when computing curvature, unless they automatically give me a unit tangent vector or something. All right, so let's see, let's compute our derivatives here. So r prime, that's 2t, 2 and 1, and then r double prime is going to be 2, 0, 0. Okay, now remember, this is all at t equals 1, right? So that means that in our case, we're just going to say this is 2, 2, 1. And this one, we don't really even need to plug t into that. We have 2, 0, 0. Okay, so first of all, let's do the magnitude of this cubed. So the magnitude of r prime of 1 cubed is 2 squared plus 2 squared plus 1 squared to the 3/2. Now with the magnitude, it would normally be to the 1/2, but then we're cubing it. So now this will be to the 3/2 instead. All right, this number in here will be 9. And 9 to the 3/2 is going to be 27. Okay, so our denominator will be 27, and that matches some of our answer choices, so that's a good omen. So let's go ahead and compute the cross product now. Okay, let's see. So we do r cross r double prime. let's see here. So we're going to do 2, 2, 1, and then 2, 0, 0. All right, let's see here. We do 2 times 0 and then 1 times 0. Well, that's going to be a big old 0. All right, now we have j. We have 2 times 0 and then 1 times 2. So that's -2. But then we have a negative by default with the j right here. And then finally, k, we have 2 times 0 and then -2 times 2 will be -4. All right, so now we're finally ready to do our curvature at 1. So the magnitude of this vector is the square root of 4 plus 16, and then we divide by 27. So this is root 20 over 27, and this will simplify into 2 root 5 over 27. And that is one of our answers here. All righty, that was a good one. Let's see, now how are we doing on time? Let's see, we have 4 minutes left. Maybe that's time enough to do 11, if we're lucky. Which of the following is an equation of the oh, let me see, thank you guys see this. Which of the following is an equation to the tangent line of this curve at t equals 0? All right, so we don't even need to do any tricks this time, no figuring out what t is, they just immediately tell us what it is. All right, so t is 0. Now, in order to get the equation of a tangent line, we need to know what point we're finding this at, and we also need to know the direction vector for our tangent line right here. All right, so let's see. So our r is tangent of t, 2t plus e to the t at e to the sine of t. I already said t equals 0. All right, so in order to get our direction vector, we need to take the derivative. Derivative of tangent will be secant squared. The derivative of this will be 2 plus e to the t. And the derivative of e to the sine of t, we need to break out our old friend, the chain rule here. All right, so the derivative of e to the something will be e to that same thing, as the derivative of e to something is itself, but then we need to multiply by the derivative of what's inside. So we're going to grab ourselves a cosine right here. All right, now the slope or the direction of our tangent line will be this with 0 plugged in, since that's our specific point. Secant squared of 0, that's 1 over cosine squared of 0, which will be 1. Then we have 2 plus e to the 0. E to the 0 is 1, so this will be 3. And then finally, for this bit right here, e to the sine of 0, well, sine of 0 is 0, e to the 0 is 1, and I have cosine 0 is 1. Okay, so this is going to be our r prime, and then this is also going to be the direction vector for our line. And then finally, we need a point on the line to specify this right here. The way we do that is we just plug t equals 0 into our r to see what point this is all happening at. So if I put t equals 0 into here, I have tangent of 0 is 0. I have 2 times 0 plus e to the 0 is 1. And then I have e to the 0, which is 1. All right, and it looks like the form they're putting this in is in terms of a vector equation. They're kind of just putting all of this into a vector. So why don't we do the same thing? All right, so this means that our tangent line of t, which will be a vector, is going to be, let's see, so we have 0 for our starting x value, but then we have 1. So we're going to have 1 times t. We have 1 for our starting value for y, and then we have a 3. So we have 1 plus 3t. And then we have 1 for the starting z value, and then a 1 for the direction. So that's going to be a t right there. And it seems like only one of these matches up with that, and it's going to be option A right there. All right. Let's see here. Do we have any more time? We have 1 minute. I do not think that's enough time to decompose an acceleration vector. So I think we're going to have to save this one for the sequel. So remember, I'm making part 2 of this video sometime tomorrow morning probably, and I'll post both of these once they're finished here. All right, let me stop the recording here.